Still in Chapter 2, Atomic Structure. 2.1 Bohr's Atomic Model. Part 2, Energy Change and Ionization Energy of Hydrogen Atom. In this part, you will learn about the energy change, Rydberg equation, and ionization energy of hydrogen atom. So, energy change. The symbol for the energy change is the delta E. Okay, this is a formula that you use in the part 1. Okay, for the electron at n equal to 1. And this is the formula for the calculations energy for the electron at n equal to 2. So the difference energy of the electron at n equal to 2 and at n equal to 1 is the energy of electron E2 minus E1. Energy change between any two levels. Okay, you can use this formula, delta E equal to the Rydberg constant in bracket 1 over n initial square minus 1 over n final square. Or you also can use this formula, delta E equal to the h nu. H is the Planck constant and nu is the frequency. Okay, this formula I have shown you in the part 1. Okay, so these two formula can be used to calculate the energy change. For the example, if the electron makes transition from the lower to the higher energy level, and the lower energy level is the n equal to 1 and the higher energy level n equal to 3. So it's starting the initial energy level is 1. So initial is 1 and the final is 3. So n final is 3. Alright. If the electron makes transition from the higher to the lower energy level, the initial energy level is 3. Okay, and the final energy level is 1. Okay. If it is absorptions, we refer to the energy electron that makes transition from the lower to the higher. When you calculate the delta E, you will get the answer in positive sign. Okay, because it is absorptions. If you calculate the difference energy for the emission, okay, or for the electron that makes transition from the higher energy level to the lower energy level, so you will get the answer with the negative sign because it is emission. So when you use this formula, you will get the amount energy with the sign positive or negative. If you get the amount of energy with the positive sign, so it shows that it is absorptions. If you get the answer with the negative sign, it shows that it is emission. But when you use this formula, it always positive. Okay, delta E equal to the h nu or delta E equal to the hc over lambda, it always positive. So the amount of the energy released by the electron during the transition is called photon. As I told you before, when an electron makes transition from the higher to the lower energy level, it will release energy in the form of photon. Photon is the light. A photon of the energy is released in the form of the light with the appropriate frequency and wavelength. It has frequency and wavelength. Therefore, the energy change, whether it is released or absorbed, can be related as, okay, by using this formula, delta E equal to the h nu, and I told you before that the frequency equal to the c over lambda. C is the speed of light, with the value is the standard value is the 3.00 times 10 to the power 8 meter per second, and then the wavelength, okay, lambda, all right, must be in meter. And then H, okay, H here is the Planck constant, and this is the value for the Planck constant. So if you use this formula to calculate the difference energy, the value always positive. Okay, and you have to make sure that the wavelength must be in meter, because the unit of the speed of light is in meter. So this is a two formula that you can use to calculate the energy change. Okay, by using the formula that has the Rydberg constant, and another one if you have the frequency and wavelength, so you can calculate the delta E. Okay, let's see the Rydberg equation. Rydberg equation used to calculate the wavelength of transitions of electron between two energy levels. So this is a formula for the Rydberg equation. 1 over lambda equal to the RH, Rydberg constant, times to 1 over n1 square minus 1 over n2 square, and n2 must be larger than n1 because it is calculation for the wavelength. So that's why the n2 must be larger than n1. And wavelength, okay, n1, n2 is the integer, okay, for the energy level. And the Rydberg constant used is 1.097 times 10 to the power 7 per meter. So for the Rydberg equation, because it is calculation for the wavelength, that's why the Rydberg equation is in unit meter. Okay, there are two value of the Rydberg constant. Another one is the 2.18 times 10 to the power negative 18 joule. Okay, that one is for the calculation for the energy, but this one is for the wavelength. So the wavelength always larger than 0, and n2 must be larger than n1. Okay, because the wavelength must be always positive. Okay, let's see example 6. Okay, by using the Rydberg equation to calculate the fault line in the Balmer series of the hydrogen spectrum. Okay, Balmer series, when an electron drops or fall back to the lower energy level n equal to 2. So the first line, when the electron makes transition from the n equal to 3 to n equal to 2. So if the fault line, it shows that the transitions of the electron from the n equal to 6, okay, 6 to 2. Alright, so it needs you to calculate the wavelength in nanometer, okay, frequency and energy. So fault line of the Balmer series, okay, you have to state that it is a transition from the n equal to 6 to n equal to 2. So by using the Rydberg equations, okay, you have to write the formula complete with the n2 larger than n1, then substitute the value, then you will get the answer in meter. But the question asks you in nanometer, so you have to convert to nanometer, and the answer is 410.2 nanometer. Okay, next, for the frequency, by using this formula, okay, this is a standard value for the speed of light. Okay, you don't have to memorize this one, okay, because it gives you in the constant value. And then, okay, you substitute the wavelength that you have calculated in the part 1. Okay, then you will get the frequency 7.314 times 10 to the power 14 per second. For the delta E energy, okay, you can use this formula because you are calculated the frequency in the part 2. So you can use, okay, the Planck constant times to the frequency you calculated in the part 2, then you will get the delta E in joule. So the delta E, by using this formula, always positive. So this is the amount of energy okay, for the transitions an electron from the n equal to 6 to n equal to 2. Okay, next, ionization energy of hydrogen atom. What is the ionization energy? We refer to the minimum energy in kilojoule per mole required to remove an electron from a gaseous atom or ion in its ground state. Okay, so this is the definitions for the ionization energy. So the equation for the example, we have the hydrogen atom in the gas phase. Okay, it only has one electron. So when it release one electron, okay, it will becomes ion H plus in the gas phase and release one electron. So this is the how much energy needed to remove the electron from the hydrogen atom. So hydrogen atom is ionized when an electron is removed from the starting from the n1 equal to 1 to n2 until infinity. Okay, by using the formula delta E, okay, you can use this formula equal to the Rydberg constant 1 over n initial square minus 1 over n final square, which is the Rydberg constant used is 2.18 times 10 to the power negative 18 joule, and the initial is 1 and n final is the infinity. So 1 over infinity is 0, so this one become 1. So the difference energy is 2.18 times 10 to the power negative 18 joule, same as the Rydberg constant value. Alright, so for removal 1 mole of electrons from the 1 mole hydrogen atom, okay, this is the calculations delta E for removal 1 electron from the 1 hydrogen atom. Okay, this is not for 1 mole. This is a energy for removal 1 electron from 1 gaseous atom. To remove 1 mole electrons from the 1 mole of hydrogen atoms, so this value, okay, for the 1 atom hydrogen times to the Avogadro number hydrogen atoms per 1 mole. Then you cancel atom, then you will get the unit in joule per mole. So convert for the ionization energy, you must the final answer must be in kilojoule per mole. So you convert to kilojoule and then you will get the answer 1312.4 kilojoule per mole. So this is how you calculate the ionization energy for the hydrogen atom. Okay, remember by using this formula, okay, you are calculating for the difference energy for 1 hydrogen atom. But to get for 1 mole of electrons, okay, because the ionization energy refer to the minimum energy in kilojoule per mole, okay, so you have to multiply the Avogadro number. Okay, finding ionization energy experimentally. Okay, this is a spectrum, line spectrum. Okay, then you can see that from the left to the right, the wavelength is increased. So this is the farthest line. Okay, as I told you, the farthest line is the first line. Okay, and you can see here the line become convergence. Okay, and the frequency is increased from the right to the left. So ionization energy is determined by detecting the wavelength of the convergence point, which is, okay, this is a convergence limit. So where the electron is ionized, is removed from the atom. So eventually the line becomes so close to each other that merge at a point. We call it as the convergence limit or continuum limit from the continuous band. So nucleus can no longer hold the electron. At this point, okay, it shows that the electrons are far from the nucleus. So we assume that there is no attraction anymore with the nucleus, between the nucleus and electron. So that's why we call it as the convergence limit. Okay, So next, let's see the example 9. So it gives you the line spectrum with the wave number. Wave number we refer to the 1 over lambda, the value of the 1 over lambda. So the farthest line here, this is the farthest one. Okay. Okay, so this is a for the last electron. Okay, convergence limits. So the Lyman series of the spectrum of hydrogen is shown above. Calculate the ionization energy of the hydrogen atom from the spectrum. So by using the formula, this formula, because it gives you the wave number, so delta E equal to the hc over lambda. So here you can see that it is a 1 over lambda here. Okay, then the Planck constant times to the speed of light times to the wave number for this point. Okay, for this point, convergence points. Okay, then you will get the answer, this one, and this is a energy for the one hydrogen atom, but for 1 mole of the electrons, okay, multiply by the Avogadro number, then you will get same value as before. Okay, but you have to give in kilojoule per mole. Alright, you will get in joule per mole, but you have to convert into kilojoule per mole. Okay, this is another way, okay, to calculate the ionization energy by using, which is using the formula delta E equal to the hc over lambda to calculate the energy for one hydrogen atom.